I see no questions, so let's proceed with the second part of the lesson related to network analysis. First of all, we won't go deep into the kind of theory or even the kind of technical details of network analysis. Many of you have taken the, for example, advanced geoinformatics course where these things are handled a bit more thoroughly. Today here we see how it can be implemented in Python using these tools. But maybe as a short motivation, I assume you see my screen, and now there should be this Screencast web map that is a tool that was developed based on a master's thesis project. Joose Helle at the Digital Geography Lab. So this is quite a cool example of the, well, shortest path problem with some additional flavor. So let's see if we would want to bike from Kumpula campus to, let's say, somewhere in Kamppi or even Central Railway Station destination. And then there's different options on how to optimize the route. So often these are based on shortest travel time, which is fine. But here the routing is done. Now this was the greenery. So in the background, there's the bikeable network and then additional parameters telling how green the route is. And then the greener the route, the kind of less costly it becomes. So then the time isn't the only factor that determines the shortest or best path. So here again, we have an origin and a destination. There's a routable network with some costs. So length of the segment, and here in this case, the greenery, and then the algorithm finds the, in a way, least cost path from A to B. So this is not a, well, Python-based tool, but the idea is the same that we will be repeating today. And then, of course, you have used the travel time matrix, which covers the whole area. So you can analyze the travel time from all locations in the region, for example, to the Central Railway Station. And behind that, there are thousands and thousands of origin destination routings that have been done and aggregated to that data set. So the methods here are linked to these kinds of problems related to travel time, distances, accessibility analysis, service accessibility, job accessibility, and so on. So we'll now start using more tools from the NetworkX module. That's the link to the documentation. So just to briefly mention some of the most popular algorithms for solving these shortest paths problems are, for example, Dijkstra's algorithm. Maybe I'll just show it quickly here. So this is now NetworkX documentation, and it tells you that this, for example, this method computes the shortest path in a weighted graph. So we have the concept of graph, which is the, in a way, route network that has these nodes and edges. And then there are indeed the nodes that are the junctions where you can turn to different directions. And then the edges are the actual segments that have then these additional costs, such as the length or other variables. And if you're curious, you can even have a look at the actual Dijkstra algorithm based on which this tool is done. So it's a function and collection of for loops. So basically the tool finds the least cost path between all the nodes in the network, and then based on that can, for example, answer what is the shortest path between two specific locations. All right. That's a kind of quick layman's summary of the algorithm in the background, and there's other approaches also to solving this problem, and the computational efficiency of these algorithms varies depending on the implementation. All right, great. So let's get started. I'm now again here in the notebook environment under lesson 6, moved to this network analysis notebook, should be available there. And you can start by checking that you have the required tools installed. So there's basic Python modules for handling file paths. Again, OSMNX will need that for fetching the data. NetworkX as a separate import here. GeoPandas, visualization tools, Pandas for data manipulation, and then some CRS checks. And then I added contextually here if we want to do a fancier map at the end. We'll continue working in the Campi as we're now a bit familiar with it. So again, as a starting point, as we're analyzing a kind of restricted area of interest, let's start by defining it. So Campi, Helsinki, Finland, apparently Campi should be enough. And we'll basically repeat what we did in the last lesson. At least start with the same approach. So we'll use this graph from place tool. We have the query, so the place name. But here, as we will want to do some meaningful analysis, so not if you're driving with a car, you can't take all the roads available in OpenStreetMap. If you're walking, you maybe shouldn't walk on the main driveway and so on. So let's check how we could actually define the network type of the network that we want to analyze. And again, I will jump to the documentation, still in the OSMNX page related to this module that handles these graph objects. So we're using this graph from place. There is a similar tool, for example, graph from point, graph from polygon. So you can have these set different ways of defining your area of interest. They are similar. Let's go back here. But now we want to use the next parameter for defining network type. And the options are here. We could have all private roads, all roads, all bike roads, all drive, so car roads, service roads, and then pedestrian roads. So here you can try whichever you like. I will take drive as the first example. So we had network type parameter equals some value. I'll run it. And then again, graph. Yep, now I have a type px. Okay, so you might remember from the last lesson, there were a bit more segments in the picture. These are now only the roads that are drivable with a car based on the attributes. Okay, and I think last year we did that lesson with this drivable network, but I think it's a bit boring because we want to promote sustainable modes of transport, reduce car dependency, and especially if you're in Campi, Helsinki, don't go there with a car if you don't have a good reason. So I prefer to use bike parameter. Let's see if that's risky somehow because we will get more data, but I tested it should work quite nicely. So I just rerun that while you guys are typing this all in. So there we go. This should be now the bikeable network from the same area. And let's work with that. I also added some more complexity because this is such a small area. And let's say if we want to route from origin and destination within this area. So who knows if the shortest path goes a bit outside our boundaries. So that is often a valid thing. And for example, with the travel time matrix, the calculations were done so that there was a buffer for the Helsinki region, then the routing was done, and then finally it was cropped to the actual area of interest. So that's good to consider if you want to have meaningful results. If you're routing from here to there, this network will route from like very long way, while in reality, there probably is some connecting segment that was just outside the border. So not to spend too much time on it, I left in some code cells, but let's do this just to kind of motivate you to always think about these things a bit further. I hope this doesn't take too much time. So what we need, or how I did this, there might be a more simple way to do this. So we learned how to get the area boundaries. So to GDF, geocode to GDF place name. And this returns the place polygon. We did this just before the break. And then if I would want to say, I want to buffer, I want to add 500 meters of buffer in order to get the surrounding road segments, I could do it. This will return the data in this geographic VGS84 coordinate system. So then as the next step, I want to reproject the data to some local projected coordinate reference system. So this is a geodata frame containing the polygon. Then I reproject it to a planar system, metric system. I'll have it in there. Geodata frame, which has a geometry column. And then all of this should be a recap for you guys. So if you then buffer, I think even 200 meters is enough. I did test this before. So this will create a bit larger area of interest for me compared to the actual CAMPI borders. And then to make it more complicated, I want to reproject back to VGS84, which is required by OSMNX. So 4326. 4326 is the EPSG code of VGS84. Easy to remember. And then when we have now this like custom area of interest polygon, we are doing this because our routing will go from one edge to the other in a way, and who knows if the shortest path goes from there. So then finally, I showed this alternative graph extraction method. So now we're using this new polygon. I hope this is not confusing. I'll just fetch the polygon first. Let's do it like this. What I did here, just split it into two separate segments. Place polygon. So here I have, what I did here was indeed to fetch the polygon, reproject it, buffer it, reproject back. So now I have this polygon object in a geodata frame, and then I can use this graph from polygon by passing the shapely polygon for it as the value and run that. If you got lost, you can just proceed with the graph object. You just download it up with the above code cells. But this is just to make the analysis more meaningful with a bit more custom area of interest. And if you have any questions, don't hesitate to ask. And that might also take a couple of moments, but shouldn't be too short. I'll type in the next one as we're waiting for the second graph to download. We already did this as well before the break. So if I now want to retrieve the edges as geodata frame, I can use this ox.graph to geodata frames. I'll pass in the graph like we did before. Before, you remember we had these nodes and edges as the results. but this time I can say that I only want the edges. Which should be clear if you read the documentation of this graph to geodata frames. I think it looks surprisingly like my custom graph is taking a bit more time to download than I wanted it, but I'm sure it will come in a couple of seconds. And luckily I have left in quite a lot of these code cells in, so we can actually discuss these and understand what's happening instead of then typing like crazy. I'm wondering, is this syntax clear to most of you, what's happening in here? In case it wouldn't be, so what's happening in here is that we have the geodata frame, then I take the column geometry, then I take, so this column in here, so this would be a pandas series. Then I take the values of that pandas series. So there is one value, and then I take the first value of that pandas series, which is then the actual shapely polygon representation. Now it went through, at least on my side. So here you can see now, this was the original area of interest. So feel free to use just this code cell for getting the graph object in memory. I now did this bit more lengthy approach of creating a custom polygon and fetching a bit larger graph in order to include these roads that are just surrounding Kamppi and might actually be the shortest path, who knows. Okay. If you're having trouble, please put the red X. I think the most common problem here would be that you just are waiting for the response from the API. But I will proceed if there's no evident issues. All right, so visualize the graph. We are fetching the edges, graph to geodata frames. Again, we can see the columns. So now I have the bike lanes. If you took the car lanes, you might have different attributes, but there's specific attributes then related to these road segments. Coordinate reference system is VGS84, and the actual contents of the data look like this. So you can see some of these highway tags here: primary roads, residential roads, cycleways. So if you had fetched the car lanes, you wouldn't have cycleways in the data. That's quite logical. I think this list actually now matches with the car network. So for example, maximum speed. Yes, it is there. Yeah. So these links should work and take you to the OpenStreetMap documentation of the tags. So let's still have a bit more detailed look into the highway column. And let's see how this works. So we have the edges, we have the column highway. We can print that. So this is a pandas series, which has 2,563 rows, so not so informative. You might have used this value counts function. So there's some warning, but we can now ignore it. There are some list types in there, which might not be now included in the result. Oh, actually they are. Yeah, so there's some double attributes for some of these lanes for some reason. But anyway, so we can see that most of these edges are now cycleways in the result, but there's also residential roads, primary roads where you are allowed to bike. So all of these will be then taken into account in the shortest paths analysis. And as the Python trick or pandas trick, this value counts is super useful. It kind of cross-tabulates the categorical values in your spreadsheet. So whatever data you have. You could have male, female, other, or these highway types, or whatever else. So the count of a category in this categorical column. Yep, and one mention still on the attributes. So this unclassified means that nobody has assigned the road type to that segment. So it just is there, but it's unspecified what type of a road is. So there are these like imprecisions in the data in terms of the attributes. And if you're mapping an area you don't know, you're not sure if that is a cycleway or whatever, it's just some kind of a way, you can tag it as unclassified. Great. So moving on, as we will be doing network analysis soon and calculating, for example, route distances, we want to do that with a projected layer. As you remember, VGS 84 represents the kind of geography, so the world as an ellipse, but we want to do distance calculations in a metric projected system, right? So OSMNX has this project graph function. You can see documentation behind this link, but basically we just pass the graph to it and it will return us a projected graph. And how does it know how to project it? It takes the UTM zone, so the Universal Transverse Mercator projection from that particular place. So for Finland, it will be UTM zone 35. That matches our longitude. Run that, and then we can refetch the nodes and edges from this projected graph in order to have them in the VGS, in this UTM projection. So if you check here, these coordinates are now these decimal degrees that are quite useless if you want to calculate distances. But here again, OX graph to GDFS, geodata frames. And here we now pass this new graph project. And I think we just can do like this. So now with this new projected graph and edges therein, the coordinate reference system is a metric system, right? That's super important if you're doing distance calculations, because if you calculate distances in decimal degrees, that's quite nonsense. And you can observe the same in here. So now you have these longer numbers in the coordinates, right? Cool. I hope you grasped this. We will need these projected graphs and nodes and edges in the following steps. There was still final code cell. So you remember the CRS objects. We take the CRS object of this CRS attribute of the edges, and then you can, with this function, print out the EPSG code, which is actually, this is now the specific definition of the projection used for this graph that's located in Finland. You can check that link if you're interested. Next section I will skip quite quickly. So there are some nice methods in OSMNX now that we have fetched the graph. So there are these network metrics that you can calculate. So centrality, density, whatever else. I'm not the best expert to explain you these network properties. Rather, I recommend that you check, for example, Geoff Boeing's work and related literature. So these sorts of density and other street network metrics are useful if you want to compare, for example, urban regions in terms of the density of the urban structure or completeness of OpenStreetMap data from another perspective. So there's a bunch of these metrics, and you can read some more information on the documentation. Some of the metrics require that you define a bounding kind of boundaries for the area. So if you run these cells, you'll get even more long list of metrics. So for example, how many nodes per kilometer and so on and so forth. But yeah, indeed, this is kind of extra content if you want to, for example, use these in your final assignment indicators. So there's Wikipedia links and indeed some scientific articles and blog posts related to this. So feel free to dive in to that. But we will now focus the rest of the lesson to this shortest path analysis. So in this graph, find the shortest route from one location to the other using a specific mode of transport. In my case, it's the bicycle. Yeah, okay. So of course, for such analysis, we need some origin and destination locations. So we are in Kamppi. Again, I'll maybe show this nominative result. So this was our area of interest. So now we should come up with some meaningful origins and destinations. There's, for example, Tennispalatsi, which is the movie theater, Ruttopuisto. I think Leppäsuo, which is the student place, it was just outside the area. So of course, if you do this custom buffer, you could route from Klusteri, from Leppäsuo to Ruttopuisto. But I chose for this example, this Maria 0, which is kind of a startup hub in Helsinki. And so what's the shortest path from there to Ruttopuisto? That's our little example. And the approach is a bit similar. What we need here is that we define the locations based on their place names. So we need the actual coordinates for these places in order to link them to the network that we have in order to do the network analysis. So how can we get that information? So we again define this query. So you can do this Maria 0 Helsinki, which is a point of interest in OpenStreetMap, and then geocode that. So there is this ox.geocode to GDF, place name. Oops, now I have some typo. Didn't run that one. Okay, but now we have a polygon and it's not so, you need to be very specific. What is the origin point? And polygon is not a point. We could maybe fetch the front door of Maria somehow, but here we will just use the central location of this polygon as our starting point. And for that, we can use the tricks we already know in GeoPandas, but before that, we want to reproject. So this is now as fetched from the API. We have the data in VGS84, so wrong coordinate reference system. So you should be able to reproject data based on your skills. So geocoded place, that's our polygon or the geodata frame. And then we have this 2 CRS, you remember? So this is now our geodata frame that we want to reproject. And you can actually do so that on the fly, if we want the same CRS as the road network, so we have the edges proji, and just take the CRS attribute. So this should work nicely. Let's see. And I again haven't place. I start making typos. The later it gets. I add one code cell to check. So now we have this UTM zone 35 also in this geocoded place as the coordinate reference system. So geodata frame name, function 2 CRS, and then we can pick the correct definition from this other layer, pass the CRS as a parameter, and then say kind of replace the geodata frame, right? Okay. Well, you can leave it as that. Okay, I hope you're following. If I'm going too fast, please stop me. Okay, so we are still working with Maria 01. We have the polygon. We have the correct CRS. So we still need the centroid. And how do we get the central point of that polygon? We again take that whole geodata frame, then its geometry, and as again we have only one row of data, we can take the centroid, and from that again the values, and then the first value. So now we have we only want if you would go and read the documentation of the tool we're going to use, we need the shapely point as input for the routing analysis, and there we have it, right? While you're typing that in, I can break it into pieces. So this part is the column geometry from this geodata frame. So, and that geodata frame only has one row of data. If we take the centroid, we have a pandas series with one value, which is the point object. And then from that pandas series, we get the values, which looks like this. So there is a shapely point object. And then if we get the first value in that array, so then we have the point that we want. Okay, so this is the same playing around with geodata frames that you probably are already rather used to, but always nice to see examples. Okay, I take that out. I hope you have that now. So we have the origin point. So basically then we can just repeat the same steps for the destination, and repeating steps is often best done using the copy-paste method. So let's just first define the place name, and then the rest of the steps are identical to the previous one. So we want to geocode the place name. Where was that? Up there. Control-C and Control-V. Then we want to reproject. That was in here. Control-C, Control-V. And then we want to get the centroid for the destination. Control-C, Control-V. So we just with this different place name, we repeat these steps, and we could even wrap this into a small function if you would like. That should work. And now we have a different point for the destination. Great. Origin point, destination point, street network. As you notice, often, again, most of time goes into preparing the data for the actual analysis. But of course, data preparation, making sure that it's valid, it covers the extent you want, it represents the features you want, so bike network, all that is crucial in order to get meaningful analysis done. So almost there. Now we still need to link these origin and destination points into the graph. And in order to do that, we want to find the nearest node in the network. I scroll up just quickly to explain further. So we have this network, and let's say our origin point would be here on the west side. So we want to find that, okay, that node is the nearest node, and from that node, the routing then starts using the graph algorithms described earlier. Where are we? Okay, so to save some time, there are some tricks you need to do. So we need the origin X and Y coordinates as a tuple for OSMNX. We will use this get nearest node function. Show that quickly to keep you up to speed. Get nearest node, here we are. So we need a graph, we need a point as a tuple, so that's why we do the step there. And it returns, well, this is now deprecated, we are using it, but we have the older version of OSMNX. So this is node to hover to update this point of the lesson, but good that we now discovered that we're using an outdated method. But let's not get stuck there for too long. This works at least in the CSC notebooks, but those following online, you might want to dig in deeper how this finding the nearest node should be done. So we have the tuple as required, and then we use this function that shouldn't work or will not work with a newer version of the tool. But it's fine. There was the graph, so we passed this graph proji. Then we have this origin X, Y, oops. And then actually we might want to define the method. Well, that's not so useful, but it works now, at least in this old environment that we have here. So what this old method used to return is the ID of the nearest node. So which node was the closest to this origin XY point in the Euclidean space, so kind of bird's distance, straight line distance. So this is the node ID for that one. And the same for the target. So you can copy paste that and change target XY. So we have a different node ID for the target node. So get nearest node, graph as the first parameter, origin XY, and then Euclidean method. Okay, I go forward. Still more pandas stuff that needs to be done. So now we have the node IDs. Then we have all the nodes. So the node IDs are these in the index and also in the OSM ID column. So how can we get those rows that represent the nearest node? So that's basic pandas trick. We have the nodes proji, and you remember this. Actually, we can use at index, and our index value will be this origin node ID and target node ID. So can even copy it from there, and then copy all of this and change target. Then again, I have some typos. Ooh, maybe I actually need to do lock to get the whole. Yes, with at you would just get one element, but with lock we get the whole row of data with that index value. All right. And here, luckily, I left this code cell in. So finally, what we have in here, it's a bit a detour of where we wanted to end up. So we want to have a geodata frame that contains the origin and destination nodes as a geodata frame. So one row per point, one row for the origin, one row for the destination. So we can construct a new geodata frame. So this is a series, that's another geoseries, and we put those into a list for the geodata frame as input. They already have this geometry column, so we just specify that that geometry column is the geometry column of that geodata frame, and then we can also specify the CRS that is the same as with the nodes Proji geodata frame. And after running that, we have created a geodata frame with these points. There would be simpler ways to do this, but it's now as it is, and at least you learn some pandas tricks on the way. So finally, sorry, Howard, if we're going a bit over time, but it's okay. Not yet 2 hours gone with the lesson. So now we can finally do the routing, and here we want to maybe stop and read the actually the shortest path function that we will be using. So now we move from using OSMNX tools to using the algorithm from Network X that we have imported. And there again, it takes the graph, so Network X graph that we have already. And then there's optional parameters. So we have the source, so origin, we had Maria 01 as the origin location. And then the target, so the destination of the routing for our shortest paths. And then we could have weights in the analysis, but we'll skip those here as the impedance. So NX for Network X, shortest path, we wanted to pass the graph. So graph Proji, then we have the second parameter was actually sometimes it's easy if you don't remember what parameters and in which order, you can also just copy them from there and then populate them with your values. So source equals to origin node ID. And actually here we are not using this geodata frame. It was just done for later saving purposes. But here we actually need the ID of that nearest node for the origin and then target node ID. And we are actually also not skipping the weight because that's rather important. So in what this refers to, we have this graph Proji and we can check the parameters from this edges Proji. And it has this length column representing the length of the segment. So that will be our cost in the analysis. So the longer the edge, the more costly the route. And then the shortest path will be the least costly path. All right. Should be fast as we have the data locally. We had the graph, we had the origin node ID, target node ID, and then the length of that segment as the weight. And checking from the documentation what we get, it returns a path. So including the source and target nodes, blah, 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 blah. And then here, list or dictionary, basically containing the node IDs of those nodes through which the shortest path goes through, right? Makes sense. So this is not yet like a GIS compatible representation of our shortest path, but we have now solved the problem of going with a bike from Maria to Ruttopuisto in this graph that we have. Luckily, again, OSMNX has an inbuilt tool for visualizing the graph. So we have OX plot graph route. We have the graph itself, based on which we did the routing, so the projected route, and then this route, which is the list of the IDs. And then I have another typo. There we go. I hope you got this bit. If you didn't, please let me know, or I can do that and then proceed. So let's have a look. So from here we can see that extending the graph was a good idea, because the graph goes from there, Maria is here, Ruttopuisto is there, but those who know the area might notice that it's a bit stupid routing at the end. It goes along the streets. One could go through the park with the bike, but this obeys the rules in the network in a way that it goes via the actual road network. Maybe if you had included all paths in there, it might be able to account for the paths that are inside Ruttopuisto. So with this routing analysis, often the first like 200 to 500 meters, there might be these extra detours due to the logic of the algorithm, or it doesn't find the front door, it goes around the whole block to your destination point. Howard, what's your opinion on the time? How much more time do I have?
I am thinking 20 minutes.
Okay, yeah, I'll do
maximum.
it in 10 minutes is
yeah.
Enough. Yeah. So this was kind of the core, or this one line of code was the core of the thing, that we have some source node in the network, but it's within the network. So this ID, from which node to which node do we want to route, and then we just pass it to the algorithm. It does the calculation. So we don't need to go code the Dijkstra algorithm here. We just use the inbuilt tool. But the tricky part is to prepare the data for such analysis and make it meaningful. And that's where most of the time went, that we prepared the network, we selected the origins, selected the destinations, turned the data into the format required by this tool, and so on and so forth. So that's often how it is. We'll continue a bit fiddling with the data and data formats to get these, for example, into a geo package for us. So here, if we want, we have this list of node IDs that belong to our route. So we can fetch those nodes as geodata frame objects from this nodes proji feature, using this lock and passing a list of index values. There we go. So this is now a geodata frame that contains a subset of this nodes proji based on these route IDs. So nodes proji lock, and then just pass the list of route IDs there. And why did we do this? Is that if we want then to create an actual like line, geographic line representation or geometric line, for those, we know how to do that using tools from Shapely. So you did this already in the second lesson. So if we pass, we need to pass a list of LineString objects. So basically what we have here are the points. In this route nodes geometry column, we have the points that should be connected to create the line as a line string. So we can do that by using the line string constructor and then getting the route nodes. Maybe do it like this: geometry column, values. So we get the column, get the actual values as an array, turn that into a Python list, and then make that into a line string. So that's now a shapely object that has those root points as the nodes on the line. Right? So geometry column values into a list, into a line string. Poof, I should have left this in there. I'll just copy paste and maybe give you a bit of time to type it in or do the same copy pasting yourself. So in order to have this line string as, for example, a GIS layer that we can print to a file, we need to turn it into a geodata frame. And we can do that by passing this root line as the data. And here it's a bit tricky always to kind of grasp how these arrays need to be passed. But like this, it will become one line of data in the geodata frame. It doesn't have any columns because this is just a line string. So this one column of data in that one row of data. So we tell GeoPandas that the name of that column is geometry. We define the CRS and we tell that the geometry column is this geometry column. That should be old news for you, but constructing these geodata frames is sometimes a bit of a brain twister. And then the next one, just to walk you through it quickly, we have now this root as a geodata frame object, one row of data, one column of data. So for the first row of data, we create a new column called OSM and OSM IDs, and then we just add the IDs from this root nodes in there just to have those stored somewhere. So if I now print that again, I have a second column with the information stored, that which were the node IDs through which our root passed. And then finally, if I want to add the length of this line, you should be able to do it like this. So root geometry length. I think that's about it in terms of syntax. Am I correct? Yes. And yes. Okay, so we did all of this in order to save the data to a file and to visualize it. This should be correct as we were in the projected coordinate system. So there you should pay attention that when you do these calculations that you are in a projected metric system if you want to get the length in meters. So luckily the following code cells should be there just for you to run through and see the data. While we wait for the buildings to download, we can also add the contextually base map there. And then I think I'll finish after we have our results on the map and guide you to some additional reading on the topic. Just copy paste from there, or I'll show this from the web page. Okay, that's running. I'll just show how it looks like in where are we? How those code cells will look like when you run them through. blah, 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 blah. We have the LineString. We have it as a geodata frame. We get some new buildings. So if we then finally, we have the projected data. Now in the GeoPandas world, we have the buildings we just refetched. You could even skip that. We have the route. We have the origin and destination nodes that we created, and you can add a base map. So then you can do whatever kinds of visualizations for your route. So just as a bit of a recap for the importance of visual data exploration and then static map plotting. So here you go. You could repeat the whole process for cars if you just go up to the notebook and change the network type, or walking, change the origin and destination locations and so on. So you could continue from here. I think my process now went through also on this side. And the next code cells will then just prepare the data for saving. You can maybe run those. There were some tricks with the list values in the data. We get rid of those. We make some nice output names, and then maybe I show it from here. So if you want to save, for example, those in a geodata frame, so you can create one common file name, and then into that geodata frame store separate layers of data. Good. So we managed to do this super simple origin destination routing in this, well, now it was 1 hour of lesson, even though I wanted to be faster than last year, but it was again the same time. And for even more advanced reading, so of course, if you want to then analyze this kind of regional accessibility analysis, make catchment areas in Python. So I recommend you check out the Pyrosum documentation. There's, for example, this pretty cool package called Pandana, which is not too difficult to grasp. Maybe I show this super quickly. So that's also something for you to think for the final assignment or future tasks if you want to do things like this. So catchment areas over large numbers of data points, or then these, where was it? There's another example of this Pandana tool. So it's a different routing algorithm for making these aggregated accessibility analysis. So that's rather nice option than if you're scaling up the process. Excellent. But I think I used my time here. Thanks everybody for listening.